Hello, I would like to welcome Vicky Fawcett onto the podcast today. She's here to talk about her research on red quasars and a bit about her work in physics outreach. So, Vicky, could you start talking about some of the work you do in your PhD?
Hi, it's nice to be here. I'm a final year PhD student in the Centre for Extragalactic Astronomy, and for the last 4 years my research has been focused on what we call red quasars. So a quasar is a supermassive black hole at the centre of a galaxy, surrounded by material that's incredibly bright, so bright that they outshine their entire galaxy. So the majority of quasars are really blue, but we found this small subset that show much redder colours, and these are what we call red quasars. And we think that they're red because there's some amount of dust that's scattering the blue light. But why are they interesting? So we found fundamental differences between red and blue quasars that suggest red quasars could be a special phase in the evolution of galaxies. So the properties we've been exploring have been predominantly radio. So obviously we see in the visible, but we can use other wavelengths to probe different properties of objects. So we use radio data, and when we look in the radio, we find very different properties between the red and the blue. And so this suggests that red quasars might be this special population and important to study in terms of the evolution of galaxies.
Okay, so do we know why the radio wavelengths in particular are sort of so different between what's observed in blue and red quasars? Like, what's so special about it?
Yeah, so we have some ideas. So in particular, we find that red quasars have enhanced radio emission. So if you look at a population of red quasars and a population of blue quasars in the radio, we find that a higher fraction of the red quasars are detected in radio. And we think there might be a link between the dust that's causing these red colours and the radio emissions. So one way to produce radio waves is from shocks. So we think maybe there's some jet or some outflow that's being launched close to the black hole at the centre of this quasar, and this outflow or jet then slams into the dust in this red quasar, and this then causes shocks, and these shocks causes synchrotron emission and therefore radio emission. So we think there is probably a link between radio properties and dust. That's our kind of current working theory.
Okay. Earlier you mentioned you think red quasars might have be a part of galaxy formation, if I heard right? Evolution.
Yeah.
All right. Could you expand on that a bit?
Yeah. So the fact that we find these enhanced radio properties, there was kind of two scenarios that people thought would link red and blue quasars together. There was either this what we call an orientation model, which would say that red and blue quasars are intrinsically exactly the same object. We're just looking at them in different angles, and that's how. So in a quasar, you have what we call a dusty torus, is this kind of donut of dust that's a little bit further out from the black hole. So some people thought maybe with red quasars we're just looking through this dusty torus, and that's where we get the dust from, that's why they appear red. But the fact that we find these fundamentally different radio properties, it rules out this scenario because the radio is not affected by dust. If it was, we wouldn't even be able to listen to the radio in our house because it would be blocked by our house. So the other scenario is this evolutionary scenario, and this suggests that red quasars are a younger phase in the evolution of quasars, or maybe even the evolution of galaxies. And kind of one model for this would be you start with galaxy mergers, so two galaxies crash together. This obviously causes a lot of gas and dust and a lot of star formation activity. So then you get this kind of very energetic starburst phase. this then ignites a quasar, but you have a lot of leftover dust from this interaction. And this is your red quasar phase. And then through jets or winds, you then blow off a lot of the dust and you reveal this unobscured blue quasar. So we have some other kind of properties of red quasars that hint that this might be the case as well. So, for example, if you look at the radio images, so what is the shape of the radio emission from these quasars, we find that red quasars prefer to have very compact, very small scale radio emission, and if they are a younger phase, you might think that maybe this is a small radio jet that just hasn't had the time to grow into a larger radio jet. So that's kind of some of the ideas we have in terms of at least quasar evolution.
Okay, so what would you say is like the difference between like just black holes in general and quasars? Like, is every black hole a quasar will become a quasar, or?
Yeah, it's an interesting question. So I said that a quasar consists of a supermassive black hole, but for example, we live in the Milky Way. In the centre of the Milky Way is a supermassive black hole called Sagittarius A star. But the Milky Way is not a quasar. It's not what we call an active galaxy. And this is just because there's not enough material at the centre of our galaxy that's fueling and feeding the black hole. So essentially the Milky Way is just not powerful enough to be a quasar. It's not bright enough. So that's kind of how we distinguish. It's more in terms of like power and brightness, and that comes from how much material is being eaten essentially by the black hole. Okay,
so do we know, like, if we know, like, I guess how quote unquote powerful like a galaxy is, like how much mass there is, can we predict like if there is a quasar, if it will be blue or red, or?
So not in terms of power. So like in our work, for example, we take into account what we call luminosity or brightness. We match our samples, so we have an equally powerful sample of blue quasars to red quasars. So we know that we're not comparing apples with oranges.
Right.
We're comparing similar systems, but the only difference is their colour, which in my opinion makes them even more interesting in the case that we think the only difference is that red quasars have a really moderate amount of dust that's causing these red colours, yet we still find a lot of kind of funky properties, especially in the radio. It's kind of suggesting that just a small amount of dust really changes your radio properties in a quasar.
Okay, could you maybe expand on some of the properties that makes red quasars different from the blue ones?
Yeah. So yeah, in my work, half of my PhD has been kind of focused on the radio properties. So we have this enhanced radio emission. It's compact. We also we're trying to find what causes this radio emission. So I've said that it's I kind of off the hand comment said it was winds or jets. But there's a lot of things that can cause radio emission. Star formation, for example, causes radio emission. And part of my work is that I ruled out star formation as the cause of these weird radio properties. So we narrowed it down to either winds or jets could be causing the radio emission. And kind of in an upcoming study, actually, that I'm working on, we're hoping to distinguish between the two, or maybe say that it's a mixture. You can have these winds, kind of outflows, and these radio jets as well. In terms of other properties, we had a student that was working on the X-ray properties. So Sophie Ego, she did a master's, a level 4 project at Durham University with our group, and she found some different properties in the X-rays, which I'm not as familiar with, but we think that red quasars have different X-ray spectral slopes, and we're not really sure what that means yet. This is quite early results. And then something else I've been working on is a link between red quasars and these other unusual type of quasars, which we call broad absorption line quasars, or BAL quasars. But don't worry about kind of the name. There's lots of weird different types of quasars. But these BAL quasars are just simply quasars known to have really, really powerful winds. So people study them because they want to study these powerful winds, because if you have these strong winds, this could affect the way that a galaxy evolves, because you're maybe disrupting star formation and things like that. So the fact we find some weird links between red quasars and these very powerful wind-dominated quasars could hint that there's also powerful winds in red quasars. But again, this is very preliminary results that we haven't actually written up that paper yet. So
okay,
yeah.
So you said that you're going to work on a study like determining whether or not it's one of those two, or maybe a combination of both. How like certain are you that you'll get a sort of satisfactory answer by the end?
Not that certain, but I mean, I think that's what makes science quite interesting, is that I won't go into the details, but it's quite a simple experiment. We're just looking, we're going to plot some radio data, and there's one scenario could cause the radio data to look one way, and then the other winds would produce a different radio spectrum. And yeah, it could be the case that all the red quasars fall into one category, and then that's job done. They're all, wind dominated, for example. But what's more likely to happen is it's going to be a bit of both. It's going to be a mixture. It's going to be a bit unclear. And I think that happens a lot in astronomy, that it's not clear cut. So I don't really think. I think maybe it's a little bit naive of us to do this whole winds versus jets. It could be a combination, but it's still a good tester to see.
Yeah, I think that is quite interesting. Like, many people might think, like, if you don't get a definite answer, then, what's the point of doing it? But, yeah, I guess a great part about science is that, trying to find the best sort of explanation for things, and sometimes maybe the best we can do is sort of rule things out, but even that's not like a waste of time, right?
No, exactly. Like part of my last paper that should be published in the next month, that was looking to see if there were any differences in like the black hole properties, so like black hole mass, black hole spin, the accretion rate onto the black hole between red and blue quasars, because what we were thinking is if there were differences with the central engine, that could maybe produce these weird differences in the radio. That could be another explanation. And we don't find any difference, or any significant difference, between, for example, black hole mass between red and blue. And so essentially that was a null result. We don't find any difference, but it's still a result because, like you said, it's ruling out one scenario. And I think over at least my PhD, from when I started to where we're at now, we're starting to get a much clearer idea of what these red quasar type systems actually are. Okay.
So how come you sort of chose to go into a PhD in like astronomy?
Oh, it was quite a windy road, actually. I didn't. There's lots of people that have these stories that, when they were 9, they looked up at the stars, and then they knew they were going to be an astronomer. But I mean, I've always been good at maths. So at school, I really enjoyed maths, and I think at the back of my mind, I always thought that I would go to university and do maths. And it was only during my A-levels that I started to really enjoy the physics, and that threw me a little bit because I then suddenly wasn't quite sure what to do. So I never made a decision. I did maths and physics. So I went to the University of Warwick, and I did a joint degree. And even then, I did a research project in particle physics one summer because I thought, the particle physics I'm really enjoying that. I think I enjoy research. And I really enjoyed the research environment. It made me decide kind of more that research is something that I definitely wanted to do. But I wasn't as keen on particle physics as I thought I was. And then in my master's, I then decided to try astronomy. People that know University of Warwick, it's very big on exoplanets, so I did a master's project on exoplanets. There wasn't a great deal of choice there. And again, I really enjoyed doing the research. I probably spent way too much time on because I did an integrated master's, so I probably spent way too much time on my actual research project than I did revising for exams, because I just enjoyed it so much. But again, wasn't sure about exoplanets. I wanted to do something a bit more powerful, a bit more, I don't know, a bit more exciting in my opinion. So I just remember doing a module that covered AGN and quasars, and decided that might be quite a cool thing to study. So it was really, I guess, the end of my third year, maybe even during my fourth year at undergrad, that kind of solidified what I wanted to do for my PhD, which might be slightly unusual. I know a lot of people just carry on what they're doing in their master's to PhD, but I guess what I'm saying is you don't have to decide from day one of university what you want to do. You can try out a few things and decide.
Yeah, I think thank you for that perspective. That's quite good to hear. I think a lot of the people I've asked about this kind of thing say they just kind of, it seems they kind of throw things at the wall until something sticks.
Yeah, basically.
I mean, I've been trying to find internships and things to get to experience some research, but it's quite hard to find anything.
I know, obviously I know Warwick a bit better than Durham, but I know Durham astronomy department, at least, they do these similar to what Warwick did, which was these summer placements. So, because I know a few people that have summer students occasionally, and that really helped me out. So if Durham, do anything like that in physics, at least they do in astronomy, and you're not sure about research, it's a good, it's 2 to 3 months, you give it a go, you either enjoy it or you hate it. So yeah, it's a good thing to do. To be honest, I missed out the part where I wanted to be a nuclear physicist for, I think that was second year of undergrad, and again I changed my mind from that. So luckily I haven't changed my mind from at least quasars. It's something I really enjoyed studying, so I've decided that's what I like doing, and that's what I want to continue doing for as long as I can, I guess.
Okay, if you all of a sudden had to stop doing your research on quasars, do you think there's anything else you'd pick?
It's still in research?
Still in research.
Yeah, basically I'm making myself sound like I was very indecisive. I guess I was. So even when I was choosing PhDs, I was very close to doing gravitational waves, actually, because it was, I graduated in 2018, so remember it was 2017 when gravitational waves were the first detection, won the Nobel Prize. They were the new exciting thing. So there were a lot of PhD positions that were you can be this team of astronomers that are going to detect the first ever gravitational waves. And back then I think it was when the neutron star binary neutron star system hadn't been detected yet, so there was a lot, but people knew that was going to happen at some point. So I was very close to doing gravitational waves, so that would probably be my answer. I still like to just see how they're going occasionally, because it's what I could have done if I'd chosen a different route.
Okay. Do they actually try to sell it to you like that, when it's, I guess, topical?
Yeah, that that was the dilemma I had, because quasars, they first discovered in, I'm going to say 1960s, hopefully that's right. There's a lot of work that's been done on quasars, and you get to the point where you do worry, am I going to get to a point where there is no new discoveries? Luckily in astronomy we just don't understand a lot of things. There's always new discoveries, and red quasars are one of these examples. That it was only, I think, a year or two before I joined Durham that they looked into these radio properties and started to actually kind of focus on red quasars in my research group. But yeah, no, it's always nice to kind of jump on these bandwagons of the current thing. I mean, at the moment, I would say it's probably exoplanets is the big thing at the moment. Like exoplanet atmospheres seems to be what a lot of people are studying.
Okay. Yeah, I guess it's quite exciting to think about like being in a field where there's like cutting edge discoveries to be made. Although, I don't know, I feel like what I've heard, it can probably be quite easy to sort of like chase the ideal of like making like a really big discovery, but like I think it's quite, you know, equally important to actually make sure you're enjoying what you're actually like dedicating your, you know, life purpose to.
Yeah, no, I know, especially with a PhD, I always say that if you're not too sure what you want to do and you do a master's and you don't enjoy it, then it's only a year. Well, in this country it's only a year. In most European countries it's 2 years. So it's not the end of the world if you essentially, I guess, I don't want to use the word waste because I'm sure you would have gained something, but just not really enjoyed a year. A PhD is quite a commitment, so I guess the one bit of advice that I got quite a lot, and I would give other people that are considering a PhD, is you do need to enjoy what the project that you're applying to, or the field that you're applying to needs to excite you in some way, because you need to be motivated to go into to do your work every day, to look at these objects. And yeah, thankfully for me, I can say I 4 years down the line, I still enjoy researching red quasars. So yeah.
Yeah, everyone. I've spoken to a few people about this, and they say like, yeah, you know, every like undergraduate comes in with wide-eyed enthusiasm, saying they're going to go into research, or going to do a PhD, and then, you know, get stamped out.
I mean, I guess the similar things said for PhD students, that everyone comes into a PhD like, I'm going to be this great, you know, scientist, I'm going to be a professor, and then a lot of people just get, you know, a few years in and decide, actually I just want to, you know, go and I guess the standard one is just go and be a data scientist. And especially since in academia you don't earn a lot of money, you do it because it's fun. So if it isn't fun for you and you can earn a lot of money doing other things, then that's kind of your choice. But yeah, it doesn't really, I don't think it's a bad thing if, say, you do your undergrad degree and you realise you don't really like the subject. University has a lot of other things to offer. You just get your degree, you make friends, you do societies, then you leave university and, you know, probably don't use your degree much, but your degree's a doorway basically to other things, and then you'll find a job that you really enjoy.
Yeah, it's like we were talking about like no results earlier. I guess, you know, finding you don't like what you do your degree in isn't necessarily a waste either. No,
like most people, like I have friends that obviously have graduated and gone into careers, and for some of them they've, you know, been in multiple jobs, some jobs they've hated, and, you know, it's taken them 2 to 3 years to actually kind of find a job that they actually enjoy. So I think, yeah, it's a bit of a myth maybe that is installed to us at school, that you should know what career you want to do from, you know, when you're picking A-levels, like, oh, you've got to pick your A-levels because you should know what you want to do in university, because you should know what job that leads to. And yes, in a way, obviously, if you're doing a science degree and then suddenly you decide you want to go into journalism, like, you might find it quite difficult, but yeah, you don't need to know the exact job you want to do. You'll hopefully just work that out with time. Yeah,
like I remember for a while when I like realised I wanted to go into like a sort of scientific career, I was like regretting doing A-level computer science over, say, chemistry or something to support physics. But looking back on it, I don't think it was so bad. Like, it was good to be exposed to something like not so, like, well, it's still quite mathsy, I guess, but, you know, not so like intertwined with maths, and like the different skills that I learned, like programming, were really interesting and actually like a lot more useful than I thought they would be, even like after finishing the A-level.
Yeah, no, to be honest, I made the mistake of, well, not the mistake, I hated programming. I found it really difficult. I really struggled, and I just had this, I don't need it, I'm never going to need it, I hate it. And at Warwick, it was a little bit different to Durham, where most of the programming modules were optional, so I just didn't take programming, so I didn't really know how to program. And then until my master's, when I was forced to program, because essentially in science you mainly use programming to take some data and make a nice plot so that you can put into your thesis or paper or whatever. So in my master's I suddenly had to quite quickly learn to program, which would have been so much easier if I'd actually learned during the undergrad, or even taken computing A-level. And now I find it a bit ironic that I actually teach first years at Durham how to program in Python. And I think back to when I was a first year, I was like, I hated it and I was so bad at it. And now I teach it. But you realise that programming, it's actually quite fun and it's incredibly useful. And the majority of STEM careers will have some aspect of programming. So I would definitely recommend learning to program and sticking with it. It would be my advice.
Yeah, I was surprised when I realised how much programming is used in especially theoretical sort of research, with models and things. I thought I wouldn't be kind of leaving it behind after A levels, but Durham are really forcing it down my throat. which is I'm glad, actually. I do like it.
It is a good thing. It's painful at first when you especially for me in first year, you're up against people that have done computing A level. So I didn't do computing A level, so they're at such a higher starting point than you are, so it just makes you feel like you're not very good and you don't know anything, but you catch up quite quickly. And once you get over the initial hurdle of being familiar with the language and stuff, it becomes a lot easier. And when people ask me, well, what do you actually do in your PhD? What do you do day to day when you sit down at your desk? It's basically just Python programming, just every day. So, because I don't do sophisticated modelling and simulations. I don't do what I call high level computing. I just I have a problem, or I want to make a graph, and then I have to just think how can I write a script that will solve that problem or produce that plot. And I find that quite interesting, actually. It's kind of like problem solving but through programming.
Yeah, it's quite funny. Part of the reason why I sort of went away from computer science is because I thought, I like programming, but I can't see myself sitting in front of a desk doing it all day. And then in science, turns out that might be what I do. But
probably.
Well, that wouldn't be so bad.
Yes, it's all right.
So I thought next maybe we could talk about things you've done in terms of outreach in physics and why that's something that's important to you.
Yes, so for me, I started getting involved in outreach first year of my PhD, and I really only started getting involved because I was quite nervous at speaking. I hated presenting. I'd have sleepless nights before doing any kind of presentation. I'd be there presenting. I'd be physically shaking and stuff. And so it was kind of a way for me to try and improve my communication and my confidence. And that's how it started. But when I started doing outreach, I actually realised this was something I quite enjoyed. And the more I did it, the more I kind of saw the need for outreach. So for me, the kind of outreach I do is we would go to schools and we do astronomy workshops with, kids. And other things I do is I give astronomy talks to the public. So in science, a massive thing is scientific communication, especially, for example, the way that my PhD is funded is actually through the scientific STFC, the Scientific Technology Facilities Council, that's funded by the government, which is funded by the taxpayer. So essentially, you know, ordinary people are funding for me to do a PhD. So part of that funding is you're kind of expected to give something back to the community. So that would be through outreach. So I like giving public astronomy talks, whether that's to university astronomy societies or to amateur astronomical societies, to like slightly older adults. But also the main way I like to do outreach is at schools. And for me, that's more because I really like to encourage women to pursue STEM. And for me, I think that's kind of bias starts from a very young age. You are kind of indoctrinated as children to, you know, like one thing or another. For example, like next time, I think it's getting a little bit better, but what I noticed as a child, I always quite liked space. I liked rockets and things. If you go to try and buy like a bedspread for a girl, you go to the girls section, it's just unicorns and pink and flowers. You go to the boys section, it's space and rockets and superheroes and things like that. So I think toys and ridiculous things like bedspreads and clothes get gendered from a very young age. And I think a story related to this is I actually got the chance to go to NASA in America, and I went to the gift shop because obviously I wanted a nice NASA t-shirt, and I went to the women's section, and the only NASA t-shirts, and this is not a joke, were either pink or they were sequined. And I actually went to one of, I was like, this can't be right, this, you know, in this day and age. So I went to the shop attendant and I was like, do you not just have, you know, the classic blue NASA logo but in women's? And they were like, I'm sorry, we only do that in men's. And I refused to buy a pink NASA t-shirt, so I actually bought a small men's top because that was the one that I wanted. It's things like that just, it's these little things, like not outright sexism, just these little kind of things that make you question, is science not for women then? If you can't, you know, you can't even buy a NASA t-shirt in a women's style. So yeah, that was quite a rambling story, but essentially I do believe in just young children seeing that women can be astronomers. It just kind of unconsciously, they're just aware that that's an option. They've seen a female astronomer, they're like, that's something I could do if I want. So that's kind of why I like to do outreach.
Yeah, I think I would agree that like there's definitely a sort of, I guess, unspoken like scripts in society, like what's acceptable for, I guess, men to go into and women to go into, like when like there's a, say, female, like, I don't know, physicist, like, well, if it was a male, like, I just wouldn't really notice, whereas anytime it's a female physicist, like, obviously I'm not going to think, they must be like less able than a man. Like, obviously I would never think that, but like it's just, I guess, something that you notice, like, you know, they're female, but like if you think about it, it's quite weird, like, in the first place, but it's something that's quite notable.
Yeah, there's things like in my physics A-level class, I was one of two women out of, I think there were like 25 of us. At undergrad level, I'm just guessing numbers now, but especially in maths and physics, it was, you know, around like 20%. On my Durham PhD interview day, I was the only woman on my PhD interview day. They do them in little batches, so I was one of 12, and, you know, walking into a room and looking and like being, I'm the only woman. Like, it's, you know, it's not an issue, but it's something you instantly notice.
Definitely.
So yeah, there is still, it's definitely getting better. I've noticed, but there's still definitely, you know, a long way to go. So, and I think that, you know, outreach is not the solution, but it's just one of the things we can do to just keep this kind of encouragement and acceptance that women also do STEM.
Okay, so I guess the other side of outreach is like, I guess, educating the public about science and things like that. So I guess that's not really like something that drove me to start a physics podcast, but I mean, that's quite a big, I guess, part about sort of casual scientific, like, things like that. What are your thoughts on that kind of part of outreach?
Yeah, so I do think it's important for us to communicate to the public, and all of this like they wouldn't understand. I think that's kind of rubbish, and I think, was it Einstein? I don't know, someone that said, if you can't explain it to a child, then you don't understand it. You can explain any sort of science to the public, and especially I think the pandemic has kind of shown the need for science communication. We've always known that it's important, but the amount of, I don't want to use the word, I'll use it, fake news kind of going around, and people with their own like weird scientific theories of like why vaccines are awful, and why masks don't work, and then actually these scientists coming forward communicating clearly to the public, like, actually vaccines work, actually masks work, here is the science, I can explain it to you, this is why it works, this is the science, you can't really dispute it. So I think the current age of misinformation, I think that's why science communication is important, and also just getting people excited and curious about the world around us, making them a little bit more open-minded to thinking about things, thinking about things in the wider context, like, where are we in the universe, where are we heading, how did it all start, kind of these bigger questions. I think it's always good for people to kind of take pause and think about that as well.
Yeah, definitely. You hear like people talk about how they don't sort of teach, I guess, the philosophy behind the scientific method and things like that in school, and maybe that's something that should be focused on more than just like naming the electromagnetic spectrum and things like that. But
it is difficult for teachers because they do have this set curriculum, but it's because there's just not enough time at school. You have to get this base knowledge in order to set kids up to go to university and then learn about it in greater depth. But the problem with that is, like you say, you have all these kids that are learning about Pythagoras. There was that classic, when are we ever going to use Pythagoras? And people just learning things for the sake of passing exams, and then just not really understanding where that actually lies in terms of why people using it to help the world, and how you would use that in science. What's the point of it all? So unfortunately, I don't know how you can fix that apart from maybe more outreach, people kind of and hopefully inspiring people that just learning some equations at school actually is a good thing, and we can use those equations for all these really cool things that from fluid dynamics to astronomy to launching rockets and just all these types of things. So yeah, I remember when doing like A-level physics from GCSEs, I remember becoming actually like quite surprised at how little I actually understood things at GCSE. Like I did like well in the exams and things, but like things like, especially things like circuits, like you learn the equations and you do them, but like really I definitely did not really know what like a volt was, or what it meant or anything like that. So I guess there is it's an argument to be made that maybe there should be more focus on sort of understanding things. I think there's definitely so my mum actually is a maths teacher at school, and so they get observed by Ofsted in the UK, where they judge teaching and things like that. And I know definitely in the last my mum was saying in the last 10 years there's been a big push to what they call deeper understanding. So it is this push to that they have realised that a lot of kids just do turn off if they're just asked to rope learn, memorise all these things, that they find that really boring, because it is really boring just to memorise a load of equations and things like that. So I think there is a push at schools to move towards more of the why. Yeah,
I think that's good. Maybe in 25 years, my kids will actually know what a potential difference is. We can only hope. Okay. I think maybe we can wrap up there. Vicky, is there anything that you'd want to mention, anywhere where people can find you online?
Yes, so I do have a website, so it's Victoria Fawcett on Google Sites, and I'm quite active on Twitter, so feel free to reach out to me on Twitter. My Twitter handle is astro_Fawcett, FAWCETT, and you can also find my departmental profile on Durham, and you can email me if you want as well, if you have any questions about what I've talked about or what it's like doing an astronomy PhD.
Okay, thank you so much.
Thank you for having me.